So we'll continue now with, we've looked at ventilation, moving the air in and out of the lungs, how we do it, how much we do it. The next thing is the gas exchange. So the gas exchange happens at the lungs as external respiration. The gases are transported via the blood to the tissues, and then we have internal respiration, which is the gas exchange with the tissues. We'll look at the respirations together because many of the same factors are at play, because it really is getting gases in and out of the capillaries of the cardiovascular system. To understand this, we're going to look at some of the physical properties of gases and the composition of the mixture of gases that make up air. So, a couple of more laws. So we had Boyle's law, which is pressure and volume, squeezing a pimple. The other two laws that we're going to deal with in this chapter are Dalton's and Henry's. Again, these laws seem self-explanatory when they're explained, but whatever. Dalton's law says that the total pressure exerted by a mixture of gases is the sum of the pressures exerted by each gas. So that's like saying the total weight that you feel of rocks piled on you is the sum of the weight of each rock. But he had the insight to realize that all gases virtually weigh the same, no matter what the atomic weight is, that it's really pressure that matters with gas. So he coined this idea of partial pressure. So the partial pressure of each gas is in proportion to its percentage in the mixture. So if the atmosphere is 20% oxygen, then 20% of atmospheric pressure can be attributed to oxygen. And that's where his insight came. Because what is going to move the gases, what's going to cause the diffusion of gases in and out of the blood, is their partial pressures in each. So it's going to be the partial pressure gradient of each gas. So if we look at normal atmospheric air, and we say that the pressure is about 760 millimeters of mercury, and that we're just over 20% of that gas is oxygen, then the partial pressure of the oxygen is 159, which is 20.9% of 760. If it was 20%, it would be 152, etc. You'll notice that there's a lot of nitrogen. Nitrogen makes up about 78 to 79% of the gas in normal atmospheric air. But we don't exchange that. So the partial pressures of the nitrogen in our blood will be the same as the partial pressures of the nitrogen in the air. Excuse me, because we don't use it. It reaches an equilibrium. And so the amount of nitrogen we take in and the amount of nitrogen we put out are the same. And it's the vast majority of the gas that we actually move is this inert stuff that we don't use. Now you'll notice that carbon dioxide levels in the atmosphere are very, very low. A half of 1%, 0.04. So the partial pressure is hardly anything, it's about 0.3. Water vapor is about 0.5%, 0.46. So the partial pressure is 3.7. Now, if you were in a really humid place, that might be 1%, in which case you would have 7.6 would be the partial pressure. And the total pressure doesn't change, so it's how big do the pie slices. And because these are percentages, they have to add up to 100%. So if humidity levels go up, then the percentage of oxygen goes down. If the carbon dioxide levels go up, then the percentage of oxygen goes down. If there are other gases like sulfur dioxide, smog, other things, that will actually add to the percentage, so the percentage of oxygen would go down. That's like why people with breathing problems like to go to Arizona, because the humidity levels are low and the smog levels are low, and so therefore there's more oxygen per unit of air, so the partial pressures are actually a little bit higher. Arizona is also low altitude, so the pressure is higher, atmospheric pressure is higher. You don't see people with breathing disorders decide to go to Colorado, because it's more humid and there's a higher elevation, so there's lower total pressure. And it's the partial pressure that actually drives the oxygen into the blood. So Henry's law, another law, says when a mixture of gases is in contact with a liquid, each gas will dissolve in the liquid in proportion to its partial pressure. And at equilibrium, the partial pressures in the two phases will be equal. So what we get here is you have a can of Coke. It has carbon dioxide in the Coke. As long as the can is sealed, the little centimeter of air at the top of the can will reach an equilibrium with the carbon dioxide in the liquid of the Coke. And it will not exchange because there's an equilibrium. There's a lot of carbon dioxide in that little bit of air. There's a lot of carbon dioxide in the Coca-Cola. You open the can, and now the air, the amount of carbon dioxide drops because it's mixing with the atmospheric air. So the carbon dioxide that's in the Coke will start to come out of the Coke as bubbles. And it will do that until the amount of carbon dioxide in the Coke is the same as the atmosphere, and that's when the Coke is flat. Right? And that's all about the partial pressures. Now, carbon dioxide is very soluble in water because when carbon dioxide goes into water, it becomes carbonic acid, which then dissociates to become hydrogen ions and bicarbonate ions. And so therefore water can hold more carbon dioxide because less of it is held as carbon dioxide. So it's very soluble. It's about 20 times more soluble than oxygen because oxygen is dissolved as oxygen. Nitrogen is very hard to dissolve, so it doesn't exchange. It takes a long time to reach equilibrium. Okay, now the exchange is going to happen because of the percentage of each of these things in the air in the alveoli. Although the pressure of the air in the alveoli equalizes to atmospheric pressure, the composition of the gases don't equalize because of the length of time. When you breathe 500 mils of fresh atmospheric air with 21% oxygen, you are mixing that 500 mils with 2,400 mils of the residual air that's there that is very low in oxygen because you've taken the oxygen out of it already. So the percentage of oxygen in the alveolar air is far lower. The percentage of water is far higher. The percentage of carbon dioxide is far higher. And that's what's going to drive the gas exchange, is the partial pressures in the alveoli. So when we look at this, nitrogen drops a little bit because, as a percentage, because there's just so much more water. Water goes from 0.5% to 6 and a bit percent. Partial pressure goes from 3.7 to 47. Carbon dioxide levels go from 0.04 to, and a partial pressure of 0.3, to 5.2% and a partial pressure of 40. Oxygen drops from 21% and 159 to 13.5 and 104. This has to be over 100 in order to have gas exchange. And so 104 is about the target. Nitrogen, it doesn't really matter what it is, but there's a little less nitrogen because there's more of the other ones. So, and it's a percentage. So what we care about is the alveoli. Now, where this becomes important is that, so say you have COPD and your residual capacity has increased. Now that means that the percentage of oxygen goes down. If it goes down below 100, now you're going to have trouble with gas exchange. If carbon dioxide levels go up, you're going to have trouble getting the carbon dioxide out of your blood. That's why there are an oxygen supplements, because then you are adding oxygen to the mix so that you can increase this percentage. That's why they're on augmented oxygen. Okay, so what's going to drive this exchange of gases, of oxygen and carbon dioxide across the membrane, is really the gradient of partial pressures. The greater the difference between the partial pressure of oxygen in the blood and in the alveolar air, the faster the exchange will happen. And the same with carbon dioxide. Carbon dioxide is much more efficient because it's 20 times more soluble, so it moves 20 times quicker. So you can get away with less pressure gradient to get the same exchange. But it also matters what's the structural characteristics of where this gas has to go. And really what that is the type 1 cell of the alveoli, the endothelial cell, the wall of the capillary, and the fused basal membranes, because that's what the gas actually has to pass through. And so you want that to be as thin as possible to have the greatest exchange. So we'll look at the partial pressure gradients first and the solubilities. So the partial pressure gradient for oxygen in the lungs is very steep. By the time the blood gets into the veins, into the vena cava, and then through to the pulmonary arteries, it's given up its oxygen to the tissues. So the partial pressure of oxygen in venous blood is around 40. The partial pressure in the alveolar air is about 104. So the difference here is about 64 millimeters of mercury. So it will reach an equilibrium really quickly, in about 1/4 of a second. The blood spends about 3/4 of a second passing through the lungs, so there's plenty of time to have this reach equilibrium. And so you're going to get then in the arterial blood, the blood that is actually in the pulmonary veins going back to the left side of the heart, it should be someplace around 104, 100 to 104, because it happens very quickly because of the steepness of the gradient. It will reach that equilibrium and stay there. Now, the partial pressure for carbon dioxide is less steep. So in the venous blood, because there's extra carbon dioxide, the partial pressure is about 45, and the partial pressure in the air in the alveoli is about 40. So the difference is about 5. It's not that steep a gradient, but because it's 20 times more soluble, that's it moves that much quicker. You don't need as steep a gradient. So you get almost the equal amounts of carbon dioxide diffusing as you do oxygen, because it's easier to move, so you need less pressure to move it. This chart just looks at those percentages. Okay, here's a concept. We don't bring blood to the areas of the lungs that we don't bring air to, and we don't bring air to the parts of the lungs that we don't bring blood to. So bringing blood is perfusion, bringing air is ventilation, and ventilation and perfusion are coupled. They've got to match to have efficient gas exchange. Now, this has a whole bunch of applications in pathology. So say you have a problem with cardiac output and you're not having the perfusion, then you won't be able to, you don't do the ventilation, and people will think that they can't breathe. So when somebody's having a heart attack, they say it's like somebody sitting on their chest. They're having trouble breathing. The same thing is true if people have COPD and there's parts of the lungs are not getting ventilated, then there's no perfusion. The arterioles constrict and they don't send blood to that part of the lungs, which then backs up and increases the pulmonary side blood pressure, the right-sided blood pressure, and so you get pulmonary hypertension. And maybe even right-sided heart failure, where the heart can't overcome that pressure. And it's the changes in the oxygen levels that cause the changes in the diameter of the arterioles. So if the oxygen levels are low, because you're not ventilating, then the arterioles will constrict and we won't bother bringing blood there. When the oxygen levels are high in the alveolar, then the arterioles dilate and we bring lots of blood there. And it happens automatically. The opposite happens with carbon dioxide. So those two things meet up. So you can imagine that if there's an obstruction, the oxygen has left, the carbon dioxide is built up, you're going to have high carbon dioxide, low oxygen levels, and both of them will cause a lack of perfusion. And this is just a chart for that. Now, the respiratory membrane is normally very, very thin, and there's a huge surface areas. But with edema, with different pathologies, this could get rather thick. Scarring, that kind of thing. And it makes it much more difficult to get this gas exchange. Normally, in physiology, it's very thin, and the gas exchange happens quite well. We'll stop this video here. We'll pick up internal respiration in the next video.